Good day, everybody. I am Anatoly Parachovnik, and I want to share with you insights from my PhD work at the University of Central Florida. I want to talk about new green ways to use carbon dioxide. Nowadays, the advances in microfabrication are astonishing. As Moore's law predicted back in the 1900s, the number of components will double itself on a chip. Today, we arrive to astonishing numbers. One Ultra by Apple consists of 114 billion transistors, and Intel Core i9 work at a frequency of 3.6 gigahertz. Such advanced electronics produce a lot of potential applications, like artificial intelligence and self-driving vehicles. On the other hand, it also produces a lot of heat, and this heat needs to be managed. In general, thermal management is an enabling technology, and this is what I want to talk to you about. Power electronics propagates in a lot of different industries. The potential applications are the automotive, consumer electronics, healthcare, aerospace, and much more. For example, new internal combustion engines need to be controlled to be efficient, and all the electrical vehicles are packed with computers. In the healthcare, we can talk about real-time monitoring of patient condition, like diabetes patients that want to monitor their sugar levels. In the aerospace industry, our planes are packed with electronics that assist the pilots, and there are companies that are developing planes. In the consumer electronics, our gaming computers are becoming stronger. Microsoft is working about cloud gaming, and the office computers are also make huge steps forward. Nowadays, there are very complicated physics that can be simulated solely on a computer. Basically, you can run a real life experiment on a computer before you realizing it in the lab or on a production floor. There are also advances in renewable energy. Besides photovoltaic cells, wind and sea energy, there are also research efforts that look into working fluids for conventional power cycles. Power plant is basically a realization of a thermodynamic power cycle. The power plants fairly stay the same for the last 140 years. This is approximately the time that they are present in our life. The first thing that you need in a power plant is a heat source. It can be nuclear, coal, or gas. Then we need a working fluid. The most common working fluid is water, and it's utilized in what is called Rankine cycle. Now, Rankine cycle, take a water, pressurize it, boils it. The superheated steam goes into a turbine, rotates it, the turbine produces electricity, eventually the steam cools down, condenses, and repressurized again. Now we have different cycles that called Brayton cycles. Brayton cycle utilize a single phase media, like air or helium, and nowadays there are cycles that look into carbon dioxide as a working fluid. In general, the advantage of carbon dioxide is higher efficiency. For carbon dioxide, the efficiency can be about 50%, while for other cycles, it's between 40 to 45%. The footprint for carbon dioxide-based turbo machinery is significantly smaller. For example, we can look at the blue turbine that have 55 stages. It produces 250 megawatts of electricity, and its typical length is about 25 meters. Now, if we look at the Brayton helium-based cycle, it has 17 stages. It produces 167 megawatts of electricity, and its size shrinks from 25 meters to 5 meters. If we look at the supercritical turbine, it has only 4 stages. It produces 300 megawatt electricity, which is higher even than the steam turbine, and its size only a meter long. Basically, we understand that carbon dioxide-based power plants can be significantly smaller. If such plant becomes smaller, we can make a dedicated power plants for different facilities. For example, a data center. So let's say we have a town, and next to the town, we have a data center. We want the data center of the town's electrical grid. We can build a power plant that only services the data center. So nowadays, new needs are emerging, like wearables, electrical vehicles, data centers, personal computers. All these new applications are exciting, give us a lot of possibilities, but it also increases in energy generation. The produced energy always can be split into two portions. One is the useful, like computational power, driving vehicles, and so forth, and the other one is heat. Now, in this case, heat is a byproduct of the energy production, and this heat needs to be managed. The engineering practice that manages heat called thermal management, and it's critical part in any decent application. Let's think about a computer that the thermal engineer didn't do good, and the computer works at about 80 degrees C rather than 25 degrees C. First of all, this computer will always be hot and it won't be pleasant to work with it. And the second thing, such computer will break after a year. I want to expose you to traditional coolants that are widely used. The first one is, of course, water. Water have high specific heat, which means that it can absorb a huge amount of energy without significant temperature change. It's chemically inert and it's non-toxic to humans. On the other hand, if we have different pollutants in the water, water became corrosive, which make it non-compatible with electronics. Now, engineered fluids were invented about 100 years ago, and the idea behind engineering fluid was to enable to work at relatively low pressures. The turbo machinery back in the day couldn't handle high pressure like it can today. So we have fluids that can boil at low pressures and at low temperature, which are useful for different applications. The problem with engineering fluid that they are non-environmentally friendly, they have very high global warming potential, and their thermal properties are inferior to water or other fluids. So I want you to think about carbon dioxide as a potential coolant, and not just a coolant, it's a green coolant. So I will explain why. First of all, carbon dioxide have global warming potential of 1, compared to several thousand of other engineered fluids. Secondly, carbon dioxide is readily available on Earth. It is a byproduct of our breathing process. The trees using it to produce energy, and it's a major byproduct of our industrial era. The humankind as a species produce a lot of carbon dioxide. In the recent years, there are debates in the scientific community what to do with all that produced carbon dioxide. One of the approaches states that we can capture the carbon dioxide and store it inside the ground in cavities that once were filled with oil or gas. What I propose is to take the carbon dioxide and to find new applications that we can use it in. And cooling cycles are one of such applications. So let's take a system concept. Let's think about a data center that we need to attend to its energy needs. So first of all, we can build a power production unit or a power plant that is small, that uses carbon dioxide, and it is dedicated for the data center, which basically needs small turbo machinery and have small footprint. Secondly, we can use carbon dioxide to attend to the building climate control system, the HVAC. Nowadays, we already have commercially available refrigerators that use carbon dioxide instead of engineered fluid to run them. Let's adapt the carbon dioxide for the HVAC system. Thirdly, we can use carbon dioxide to cool our electronic components on a rack level, hard drive, and other components that are not significant heat generators and can be attended in a rack unit. And fourthly, we can also introduce carbon dioxide into a component level. So we can produce microfluidic based cold plates that will draw the heat from CPUs and GPUs, traditionally components that produce high amount of heat. Now, drawing the heat on the chip level will reduce the size of the entire cooling system. Now I want to explain why carbon dioxide is so unique. And to do it, I will use a phase diagram. Phase diagram shows us the different phases of the fluid as function of pressure and temperature. At low temperature, we have solid carbon dioxide, regardless the pressure. In the intermediate temperatures, we can have either liquid or vapor carbon dioxide, and it depends on the pressure. High pressure, the carbon dioxide will condense and liquefy. And at low pressures, it will vaporize and become a vapor. If we will increase the temperature even higher and slightly crank up the pressure, we will have a supercritical phase. In the supercritical phase, there is no distinct difference between liquid and vapor, and it gives us very interesting insights. The two interesting points are the triple point and the critical point. The triple point is at minus 57 degrees C and at about 5 atmosphere. At these conditions, all three phases can coexist. You can find both solid, liquid, and vapor phase in a single jar. And the second point, that is the most important one and which make the carbon dioxide unique, is the critical point. The critical point of carbon dioxide is at 31 degrees C, which is in a very close proximity to our ambient temperature, which is 25 degrees C. And the pressure is 73 atmosphere, which modern days turbomachinery can handle fairly easily. Now I will dive a little bit more into the specifics and I will explain why the critical point is so unique and we want to work at this point. To do that, we will look at the specific heat and Prandtl number. The specific heat shows how much heat we need to absorb in order to change the fluid's temperature by 1 degree. We see that liquid carbon dioxide have a specific heat of about 5. However, a supercritical carbon dioxide at 31 degrees C, the specific heat spikes to about 100, which means that we can absorb more heat while we're increasing the temperature only by 1 degree. We see that this spike effect of specific heat still happens at 33 degrees C and 37 degrees C. The second value, Prandtl number, is the indication of how fast the heat will be absorbed. Here at 31 degrees C, at the critical pressure and temperature, we see a high spike. If for a liquid, Prandtl number is about 1, here we jump to higher than 30. It means that we can absorb heat much faster at the critical point. So to conclude these two figures, higher specific heat means that we can absorb more heat. Higher Prandtl number means that we can absorb the heat fast. The next step is to look at the hydrodynamic properties of carbon dioxide. Here we will talk about density and viscosity. Density, liquid carbon dioxide is fairly close to water, between 700 to 800 kilograms per meter cube. The gaseous phase of carbon dioxide is low, between 200 to 300 kilograms per meter cube. However, if we pressurize the gaseous carbon dioxide and reach the supercritical phase, the density will jump to the levels of a liquid. So if we pressurize gaseous carbon dioxide, its density will jump from 250 kilogram per meter cube to 750 kilogram per meter cube. It means that we can place much more carbon dioxide in the same volume. The other thing that we should look at is the viscosity. The viscosity is basically the pumping power that we need to apply to circulate the fluid. Think about a syringe that you want to push out the fluid. The syringe is filled with air and the syringe filled with water. It's totally understandable that it will be harder for us to push the water out. Now, the viscosity of water is about 100 times higher than the viscosity of air. This is the reason why it's much harder for us to drive the water out of the syringe. Same goes for carbon dioxide. Liquid carbon dioxide is about between 60 to 80 micropascal seconds, while gaseous carbon dioxide is about 20, which means that gaseous carbon dioxide have 4 times lower viscosity, which means that we will need a lower pumping power to drive it. If we will look at the red line, we see that when we transition to a supercritical phase, the viscosity of carbon dioxide drops from about 70 to about 20. Which means that the viscosity of carbon dioxide in the supercritical phase is fairly gaseous-like. Now, this is the confusing thing. In the supercritical phase, we have density that is liquid-like, but the viscosity is gaseous-like, which means that we can circulate a lot of fluid with fairly low pumping power. So to recap, when we transition to the supercritical phase, especially around the critical point, our specific heat spikes, which mean that carbon dioxide can absorb a lot of heat. The Prandtl number also spikes, which means that the heat is absorbed fast. the density goes up, which means that we can accommodate a lot of carbon dioxide in small volume and our system becomes smaller. And the viscosity drop, which means that we don't need high power to actually circulate carbon dioxide in the system. If you are intrigued, I will produce more videos. In them, I will describe setup design and assembly. I will talk about flow boiling of carbon dioxide, its characteristics and patterns. I will talk about subcooled bubble dynamics. We will basically see how the bubbles form and how they propagate. It's important for design of different turbo machinery. I will talk about thermalization mode shift, which is very interesting physical effect that I hope in the future will have a lot of applications. Effect that was believed to be present only in the microgravity, but we also discovered that we can see it in microsystem on Earth. I will talk about pressure drop and Joule-Thomson effect, which can further enhance the ability of carbon dioxide to absorb heat. And eventually, I will also talk about critical heat flux and post-critical heat transfer coefficient and more. Thank you for listening. See you in the future. Stay tuned.